I didn't cover the last two topics of chapter 16 last week, so I want to do a video recording for these two topics in this chapter. First, let's talk about collision theory. You may wonder, how can a chemical reaction really occur? This can be explained by the collision theory. The collision theory states that molecules must collide in order to react, and for a successful collision, existing chemical bonds are broken and a new chemical bonds are formed, and therefore the reactants can transform into the new product. This is called the collision theory of reaction. Here is an example of the collision theory. Nitrogen gas and oxygen gas, in order to form the product, they must collide. Then after the collision, then the nitrogen monoxide can be formed, or nitrogen gas and oxygen gas can transform into product nitrogen monoxide. This is also called nitric oxide. There are three factors that can affect the reaction rate according to the collision theory. The first factor is frequency. When we increase the frequency at which the molecule collide, we increase the rate of the reaction. The more collision the molecule have, the greater the odds that the collision will be successful, and therefore the more chance the product can be formed. The second factor is energy. The molecules must collide with enough energy to form the new bonds. If the energy is too low, no new bonds are formed, and therefore no products are formed. In addition to frequency and energy, the orientation of the molecules is very also important in order to have the reaction to occur. The orientation must be favorable for the so that can drive the reaction. So let's take a look example of the collision orientation. There's scenario A and scenario B. In the scenario A, you can see that the position of nitrogen, or its orientation, in a way that is very close to ozone molecules. And because of this orientation, nitrogen can react with ozone molecule, forming the product nitrogen dioxide. In the scenario B, you can see that nitrogen orients away from the ozone, and therefore it created ineffective collision, and now we see ozone, and therefore the product, like it's over here, the nitrogen dioxide, was not generated. Besides all the three factors that can help with the collision, there are other factors that also can affect the reaction rate. First is the reactant concentration. As we discussed in the factor that affect the collision, that are frequency, energy, and orientation. What can change the frequency? And you can see that to increase the collision frequency, we can increase the concentration of the reactant. As we increase the concentration of the reactant, the molecules are closer together, and therefore they collide more frequently. The more collision they have, the faster the reaction. How about energy? We know that temperature and energy are correlated. If you can increase or decrease the temperature, you can change the amount of energy of reactant. If we increase the temperature, we can increase the energy of reactant. And therefore, the rate of reaction can increase because we increase the collision frequency and the collision energy. The other factor can affect the reaction rate besides the concentration and temperature is catalyst. Adding a catalyst into a reaction can increase the rate of reaction because the catalyst can increase the number of effective collision by creating a more favorable collision orientation. Now, a catalyst do not consume in a chemical reaction. It do not participate in a chemical reaction. It just changes the orientation of the reactant, and it make it more effective collision. Now we talk about energy. Then energy usually you can see through an energy profile. Here is an example of energy profile. The y-axis represents the energy and the x-axis represents the progress of a chemical reaction. The energy required for reactant to achieve the transition state is called the activation energy, which is the higher energy in an energy profile. So on the left side here, you can see it shows the energy of reactant, and the right side of the transition state, or where the activation energy is the energy of the product. The difference between the energy of the product and the energy of the reactant, we call it heat of reaction. Now let's take a look at them. Look at more deeply into an energy profile of a chemical reaction. For a chemical reaction, the reactant must collide, as we said earlier, with sufficient energy to react. This energy is required to achieve the transition state, required to form the product. Without the sufficient energy, the reaction does not occur. Here the example of the reactant nitrogen and oxygen. In this scenario, in this figure A, you can see that nitrogen and oxygen do not have enough energy to go over the transition state, and therefore you can no products are formed. So like in air, because nitrogen and oxygen, they don't have enough energy, and therefore no products are formed. Now, in the case that you have it in a hot car, if the nitrogen oxygen that is captured in a hot car, it have enough energy that can go over the transition state, and therefore it can form a new product. In this example for nitrogen oxygen, the nitrogen monoxide form when they are in a hot car, because the temperature in the hot car, it provides enough energy for the reactant can go over the transition state. So when we talk about energy, it usually is correlated to heat. It can be released or heat can be absorbed from the system. When heat is absorbed from a system, we call it an endothermic reaction. In the endothermic reaction, the delta H or heat of reaction is always a positive value because the heat of the product is higher than the heat of the reactant. On the other hand, when heat is released from a reaction, we call it an exothermic reaction. In the case of an exothermic reaction, the heat of the reaction or delta H is a negative value because the heat of the product is smaller than the heat of reaction. So therefore, when you take the difference, it should be a negative values. Now, if you add a catalyst, how catalyst involved in the energy profile. You can see here, for the example of hydrogen gas react with oxygen gas forming water. The reaction profiles here show the effect of the catalyst in this reaction. And you see here on the blue line is the energy profile with a catalyst, and the solid red line show the energy profile of the same reaction but without a catalyst. You can see here the activation energy in the case of without catalyst is higher than the activation energy in the case with a catalyst. Now, because the activation energy in the case of with the presence of catalyst is lower, that give hydrogen and oxygen a chance or giving up that their energy is higher than or equal to activation energy, and therefore the reaction can occur to form water. Without a catalyst, hydrogen and oxygen do not have enough energy to go over the transition state, and therefore no products are formed. Now for this reaction here, the catalyst can be a flame or spark, and this will be an instantaneous. It can cause explosion due to a huge amount of heat generation. However, you can use zinc dust. This also can be used as catalyst that can help to provide the favorable orientation, give effective collision without any explosion. So this is the end of chapter 16. I will post it on YouTube so you can view it.